Hello, our topic is emotion identification of esports athletes from voice recordings. We are a team of 8 people and we've done it. Okay, so let's go. So the problem here is that in data analysis of esports, it's quite difficult to understand several things. So what we do have that esports players, they are subject to very stressful situations. Although they are highly trained specialists, they do have problems when they meet tough decisions. So there is not much things available about their body's response, physiological response to the stress. To evaluate it, one might use several sources of data. That would be myography of their muscles, their heart rate, their respiratory rate, and so on and so on. The thing here is an activation of sympathetic nervous system, which is, in short, a fight or flight response. So not only there is a physiological excitement, but also there is psychological. There are psychological effects. So these psychological effects, they're usually assessed with rather lengthy quizzes to understand the emotion that one person has right now. But it's quite difficult to do during an esports match. So what we opt to do is to analyze the voice and which emotion it conveys. So basically, while esports play the game, esports athletes play the games, they communicate with each other constantly. And they do that with their voices, so we can analyze that by recording. But it is not very clear how to do that exactly, because although there are very many loads and loads of different algorithms to parse for what has been said, there is not much algorithms that evaluate the emotion of what's been said, given the circumstances in which it was made. So we have a data set that was gathered during a single elimination tournament of a game Counter-Strike Global Offensive. This tournament was played by semi-professional teams, and we've recorded every single communication of every player there was. And then we given off this data to 3 psychological experts to evaluate what emotions they were conveying with their voices. And with that, we have a labeled voice data set. And we also have a set of data of what was going on during the game in the Counter-Strike. So our data set consists of these 2 parts, voices and context data, or in-game events, such as shots fired, footsteps, elimination of a player, if there were planted a bomb, and so on and so on. There are very many things, and so many features actually are very this suits solution with deploying techniques rather nicely. So, but it's not very clear how to do that exactly, because there are 2 ways that we can approach classification of a time series, especially voice. One thing we can do is to evaluate it as an audio series, a 1D array, as a signal, basically. But also, as this is a voice recording, as this is an audio, we can do a spectrogram with predefined window lengths, with predefined stride, and so on and so forth. And this spectrogram, it's actually an image. So we can use So we can use classic techniques like convolutional neural networks and so on. But with audio series, all we can do is apply transformers and LSTMs. So basically what we do here is we prep the data by cropping every recording into 3 seconds intervals. Every interval has its label of 10 emotions that were listed on the previous slide. And also all of it has a contextual data of what was going on during the game. So next, we are going to pitch in about the models that we were using during this project.
Well, during our related work analysis, we have found that there are plenty of works that analyze the audio sequences as 1D arrays. And there are plenty of works that analyzes the audio emotions and try to classify them. However, there are not so much of such papers that classify the audio recording as an image, and more precisely the spectrogram. So let us start with the audio sequence modeling. During our analysis, we took 3 models, 2 LSTM models, and 1 convolutional neural network with 1D convolution layers. So basically, we took the 2-layer LSTM as a baseline, and the resulted accuracy for our baseline was 54%. As you can see from the slide, the 1D convolutional network with 4 blocks of convolution, batch norm, and ReLU activation and max pooling resulted in a slightly higher accuracy rate, but not so much. The biggest improvement that we got was the LSTM with attention. The attention mechanism, firstly presented in the paper of Attention is All You Need, simply shows the model to which parts of the sequence in the past to put attention the most. Therefore, such an approach, on one hand, improves the accuracy of the model, and on the other hand, it also improves the stability of the model. So as it can be seen, the LSTM with attention shows 9% higher accuracy than LSTM with only 2 LSTM layers. Well, now let us move to the spectrogram-based picture classification of emotions. Well, the first model was a simple convolutional neural networks with 3 2D convolutional blocks. Such a network is very popular in the simple image classification. But the disadvantage of its simplicity is the low accuracy. It was around the baseline level of 56%. Another approach was to use DCNN with the ResNet 18 backbone, which is simply the classical ResNet 18 with residual blocks, with the accuracy of 71%. And the best result that we achieved was gathered on the VGG so-called network. What is that? There is a VGG network on which the transfer learning was applied. So we took the pre-trained VGG and fine-tuned it for our task and on our data. As you can see, it simply consists of 2 types of blocks and 4 blocks in total. So in the result, the best accuracy that we got was the 84% for 9 classes, which is pretty impressive. Well, to sum up, During our analysis, we applied different augmentation techniques to increase the number of observations, the number of audio recordings in our data sets for models to have the higher accuracy. So as I have said before, we applied different approaches on solving the speech emotion recognition classification problem, the audio sequence-based modeling and the spectrogram image-based modeling. We also have significantly improved over our baseline, and we got the results that are pretty higher than in the papers, in the previous papers. But still, there are a future of work, the future development, and a lot of work that can be implemented to improve the results. For instance, add text-based information about the speech to make the decision process even more better. Well, that is all that we wanted to say for today. Thanks for your attention.
And cut the recording.